In the 4 videos detailing transfer functions, how to convert from an ordinary differential equation to a transfer function, one of the examples introduced was the quarter vehicle suspension. So this is a mathematical model, is effectively a second order mass spring damper. You can see here force is the input, the output here being displacement, and you have your stiffness term here and your damping coefficient. So the model and also your mass here, so mass, damping, and your stiffness. So quarter vehicle, so this could be used to effectively mathematically model, very simple model, mathematically model maybe the front left of a vehicle. Again, very simple model, and the models do increase in complexity from this, the actual model you would actually use. This is a good starting point. So stage 1, the Laplace transformation. So if you're not familiar with the steps and some of the equations, and the equations that I'm going to use here are equations 2, 2 and 2, 3 that are taken from this video, from this set of notes or this video here. So the two equations here for a first order derivative and a second order derivative. So if we apply these, so you can see here we've got the second order derivative here. So you can see that's there. So that second derivative effectively becomes s squared y of s. In our case, those x of t here, so it becomes x of s. Okay, just slightly different notation for the output. First derivative, so you can see here we've got dx of t over dt. Again, just we're using x instead of y. So dy of t over dt. That effectively becomes s y of s. So you can see down here, so if I'm looking at this equation, you can see here we've got m. So m here. Then we've got s squared x of s, because we've just transformed the second derivative, plus c, so your damping coefficient there, and then the dx of t over dt becomes capital X of s. Okay, always remember when you do the transformation of this, well, y of t here, it becomes capital Y of s here, and likewise this x of t becomes capital X of s, plus k, okay, because obviously we've got to keep these variables, plus then this x of t becomes x of s, and f of t becomes f of s. Okay, it's as straightforward as that. So converting from the time domain to the complex frequency domain known as Laplace. You'll notice here x of s is common for all these terms. What we can do is move that outside of a bracket because it's common for all. Then mst plus cs plus k. Okay, so that just simplifies it. And you'll see why we simplify it in that form when we get on to the next stage, which is stage 2, which is the transfer function. So if you remember from this set of notes, if you can't remember, watch this video, so part 3 or 4. And what we want to do effectively is rearrange it such that it's this Laplace transformation here is in the ratio of output over input. So we can effectively algebraically manipulate this equation, which we can do when we're in the Laplace domain. Can't do that in time domain, and that's one of the benefits of moving into Laplace. So to rearrange this that we've just determined as transfer function form given by equation 2.5, again equation 2.5 is on these slides. What we want to do is multiply both sides by 1 over ms squared plus cs plus k. Okay, so multiply both sides, and this here is effectively what you will get. Then multiply both sides by 1 over fs. So you can imagine if you multiply and obviously both sides by here, it's effectively cancelling. It just becomes 1 over ms squared plus cs plus k, and this will become x of s over f of s. And what I've done here is I've used the notation G subscript P for process because it's the quarter vehicle model. So G subscript P for process is equal to, and then this transfer function here. So that there is our transfer function. Okay, so all we've done, we've gone from ordinary differential equation, time domain, used these rules here. So effectively d over dt becomes s. And then rearranged it into this form, well, simplified into this form, then rearranged it into this transfer function form. Then finally, what we can do, and the reason, one of the reasons obviously we rearrange it into this form is because what we're interested in control is inputs and outputs from components, subcomponents, systems, or whatever you want to call them. So in this case, the input here of f of s, the process is modelled by this second order transfer function, and obviously which its mathematical equivalent was at the starting point, and then the output here is the displacement x of s. So I hope this video has been useful. If you have any questions, please feel free to contact me or put a message in the comments. Thank you.